and then you put a comma and put a 0 after they make it a 30. So you say now, how many times does 5 divide into 30? It goes 6 times. So that value is exactly a repetition of this value here. And I would like my students not to do this repetition, just do it once because it will save you examination time. So that is exactly that. Not if you're asked a question that will need you to put up such information, don't put both of them. If you put this number can be written as 0.6 delta O, and that one can be written as 0.4 delta O because the 5 doesn't divide into 2. You put a 0 and a comma, and then you say 20. 5 goes 4 times in 20, and that gives you 0.4. So you don't need both of these. You need only one set. And importantly, this has to be negative if you like. Inside the diagram here, the negative sign is not shown, but from your mathematical point of view, you know that if you go below your 0, then you go to negative. So you can assume this to be a 0, although it's a net energy average of something, but that will be your frame of reference in physics. That you're starting with that, then you're ending up there. So your energy will be the gap between the two, and this will be the energy gap between the two. So essentially, this is negative 0.4 delta O, if you like. So importantly, in an octahedron, 3 orbitals are stabilized by minus 0.4 delta O units. Please always put the units. And these ones, the set of 2, are elevated 0.6 delta O units. This is very important. And the dotted line that I was talking about, that it is actually the center of gravity of these orbitals in their unsplit state, is called the barycenter. The barycenter, please get a proper definition from your book. The barycenter would be the center of gravity of the d orbitals in their unsplit state. Okay, then, and it measures, or it's a relative point where you can measure the stabilization of some orbitals and the destabilization of other orbitals as such. So let's look at deeper into the parameter that we have seen there, that split that we said the d orbitals undergo under the influence of an octahedral ligand field, which we called delta O, or we called 10dq. Very importantly, it says that if we have got electrons in the d subshell, then those orbitals or those electrons in the presence of an octahedral, those ligands or those electrons will start occupying orbitals from lowest ones. The T2G will be the first to receive electrons. It can be 1, 2, 3. Remember that if you've got a set of 3 equal energy orbitals, your Hund's rule applies. You don't just populate them with electrons without considering Hund's rule. Hund's rule says that if you've got equi-energetic orbitals, you put electrons 1 by 1 in each one of them until each one of them is occupied by 1, and then you can start pairing them. You don't pair them before you complete the set, because of the fact that the electrons are negatively charged and they repel each other. They will try to avoid sharing the same space as much as possible unless they are forced to do that. So the important thing is consider Hund's rule and extend that to your Pauli exclusion principle. When you start having more electrons, then you can understand what's going on. So this is very important, that electrons can occupy both the the T2G and the EG set. And when you have that, you can write the octahedral electron. Say, for instance, I think up to the lecture that you had with Mr. Maswanganyi on the Wednesday, emphasized the d electron configuration, that you have to quantify the number of electrons that are available in the d subshell that you can use to calculate or count the number of valence electrons to deduce whether a complex would be stable or will not be stable, whether it will accept electrons or whether it will donate electrons in order to be stable, or whether it can form metal-metal bonds in order to be stable. That is essentially, you were just focusing on the d notation, but in this case now, you're considering where those orbitals are in the particular coordination geometry, which is an octahedron, that you've got 3 orbitals, which can be occupied, of course, by a maximum of 6 electrons, if you like. This is similar to your p subshell in the main group elements. That can be, because it's 3-fold degenerate, each orbital can be occupied by a maximum of 2 electrons, and that will make a 6. That can be occupied by a maximum of 4 electrons. So definitely electrons in an octahedron will be assigned or distributed between these orbitals. They're no longer having a D character, they've got a T2G and EG character. Please, we'll have to communicate a lot on this so that it becomes second nature to you as well, and not just a book thing. But it is important that the electron configuration in an octahedral complex will be designated as the number of electrons in the T2G set and followed by the number of electrons in the EG set, which is what I've given over here, right? As T2G X, it means there are X electrons, according to this electron configuration, there are X electrons occupying the T2G, the lower energy orbitals, and there are Y electrons occupying the EG set. And as a result, we have seen that there's an energy gap of 10 dq or delta O between the T2G and the EG. And so the preferential occupation of these orbitals with electrons allows stabilization of transition metals, and that is essentially quantified in terms of what is called the crystal field stabilization energy. As the title of the lecture slides talked about crystal field theory. Initially, when these physicists, actually, because this theory has been designed or was discovered by physicists and not chemists, it became a tool for the chemists who developed to a higher level in any case. But initially, the discovery was by physicists. And it was based on really crystalline materials that you've got a metal cation bonding ionically with a non-metal anion. And just consider things like sodium chloride, because they form very crystalline substances as such. And this is how the name itself came about. It doesn't mean that we're looking at crystals in this case. So that stabilization energy is measured or is driven by the distribution of the electrons in the T2G and the EG set. We have seen in the previous slide that the T2G, from the T2G, or the gap from the T2G to the EG is 10 dq. So that, or is delta O. So you've got increases in energy that are characteristic of delta O. Let's go back to the slide I would like to refer to. This is the number we're talking about. The T2G orbitals are stabilized by negative 0.4 delta O. And that is what you're seeing there, because we said there are X electrons in the T2G. So you take the number of electrons, multiply them by the amount of stabilization, which is minus 0.4. And then you've got Y electrons occupying the EG set. And you know that relative to the barycenter, the EG is elevated 0.6 delta O units. So you're taking then the number of electrons in the EG and multiply that by that. This is the equation you're seeing here. So it's a general equation that you can use to calculate, depending on the electron configuration of the transition metal in a particular complex. You can work out the crystal field stabilization energy using the stabilization amount multiplied by the number and the destabilization amount multiplied by the number of electrons. And the units of that should always be accompanied by delta O. If you don't write delta O, then the value is not the same. It's not correct, so you'll be marked wrong. So please keep track of that, and let's keep communicating as much as possible to make this subject easier, because now we're doing this by remote. We don't meet at M block or somewhere. So very importantly, application of this for the crystal field theory, it's very trivial in certain cases. Look at, if you have got electron configurations, or D electron configurations ranging from 1 to 3. I've said that the D orbitals in an octahedron split into a set of 3 orbitals, lower energy, and a set of 2 orbitals, which is higher in energy. So obviously, populating these orbitals in an octahedron with electrons will start from the ones of lower energy, which is the T2G, and we start. So if we've got only 1 electron, there's no way that it can go anywhere. We don't have to think twice. It's going to go into the T2G. It's going to occupy one of the T2G orbitals. If we've got 2, we will remember that, oh, now we're putting 2 electrons. We put them as a pair Or do we put them one by one? And we said, oh, Hans' rule says that if we've got orbitals that are equal in energy, we have to populate them individually with one electron before we can pair them. So we'll have two unpaired electrons occupying two of the T2G orbitals. And then if we've got three, we'll have one electron for each of the T2G orbitals. So that case is just obvious. There's no way the electrons can go. They will occupy those orbitals like that. But immediately we start going beyond 3 electrons. I've got a gap of D4 but it will become obvious to you as you do some practices on this section here. From the fourth electron has got a chance now. You have got 4 electrons. Look at the splitted parameter. Okay, you have got 4 electrons. Now, 3 electrons are obviously going to occupy the lower energy orbitals here. But if you've got the 4th electron coming through, the 4th electron has got a chance of occupying the same orbitals that are occupied, right? That means that it will have to share with an orbital with one of the orbitals that are already existing there. And consequently, if you have to share, or the orbitals electrons have to share an orbital, it means that you must pair them. They must be spin paired according to one of Pauli's exclusion principle, right? So definitely 2 electrons. So that is the first option, that an electron, that 4th electron, can say there are 3 electrons already occupying here, and I'm doing 3rd here. I can't share a room with any of the people on campus here because I'm a 3rd year student. I deserve a single room. Now, because this part over here is already populated, I'm going up. So the 4th electron has got a chance of either pairing with other electrons that are existing in there or occupying a higher energy level, e.g. So we'll have to look at or study the driving force that makes an electron either occupy a low energy and doesn't have an option of going up there, or why or how an electron can afford to go to the high energy level. So that is very important. From this slide here, we will need to know what is it that makes the electron to preferentially pair rather than going up in a vacant room. Everyone wants to be privacy. Everyone wants to be in a single room. But pressures, you must all pair, right? So I'm doing a 3rd year, so I deserve a single room. This student is political in any case. And then he gets there, he gets a single room. But sometimes, depending on the environment, this student may want to be in a single room, but will not afford to go there, either monetarily or because of the costs that do not allow him or her to go there. So please, let us now look into what really makes that a decision on that distribution, which is something that is not covered by the valence bond theory that you guys have covered in the previous course with either Prof. Mudibane or Mr. Mbokani. You've extensively done the valence bond theory, and it is able to really explain certain behavior, but not as much as what properties you see. So let us look at a D4, which is a simple case where we start having more electrons than the orbitals in the T2G set. Now, in one case that is called a weak field case, you've got the splitting energy, that is your delta O, the gap between the T2G and the EG being less than the pairing energy. Remember that if you pair electrons, because electrons don't like each other, you'll have to work. There has to be a certain amount of work that really makes the 2 electrons to pair. And this is why you have to reverse one of the wave functions so that the next electron will have to face downward. Because this electron pairing or electron pairing energy is very important, because an electron will say, I don't want to pair with this guy. But now, can he afford to go to the other one? That's a big question. So importantly, the relationship or the interplay between the amount of splitting that happens in the d orbitals and the pairing energy, or the amount of energy that you need to pair the electrons, will determine whether the electron can go up to the EG set of orbitals, or will have no choice but to share a room with the other electrons in the T2G. Right. So in this case, we see that if it is very expensive to pair, if the pairing energy is too high, then simply the fourth electron will go to the EG because it's smaller energy, right? It is smaller to travel from the T2G to the EG set rather than pairing, because the amount of pairing is going to be expensive because the pairing energy is large compared to that. And when that happens, you see your D4 electron configuration now in an octahedron, they were transforming as the T2G with 3 electrons and the EG with 1 electron. And such a case will have all the 3 electrons in the T2G with parallel spins. Their spins they will all spin up, if you like, because you've got an up spin and a down spin when you're making pairs of electrons, if you like. So importantly, the orbitals, the electrons in the T2G will all have parallel spins, will have pointing upwards, all of them, and the one that goes to the EG will also point upwards. And as a result, you've got 4 electrons that are having the same speed, pointing upwards. If you've got the ms value of a half for each one of them, then you've got a half multiplied by 4, which is the spin state of a 2. And that makes the particular compound very paramagnetic because it has got the most unpaired electrons, if you like. And consequently, such a compound would be called a high spin compound because there's minimal pairing of electrons, and the spin state, the electron spin will be a maximum. And as a result, such complexes or such compounds will be attracted by an externally applied magnetic field because they will be magnetic. An electron is a mini bar magnet, if you like, and it can be picked up by a magnet. So in order to calculate the crystal field stabilization energy following the occupation of electrons as reported in this case, that in a weak field, it is easier to access the high energy EG orbitals rather than having the electron pair with the others in the T2G. And the amount of energy that will be expanded in that case will be 3 electrons that we have in the configuration multiplied by the amount of stabilization that the T2G undergoes in an octahedral field, which is minus 0.4. Plus now the number of electrons in the EG set, which is 1, multiplied by the amount of destabilization that accompanies an octahedral complex formation, which is 0.6 delta O. So you're multiplying each one. I've just put delta O outside here because it's a common factor. It appears in all of them, so I've put it outside there. So importantly, you've got minus 1,2 plus 0.6, that gives you minus 0.6 delta O. So this is the amount of energy associated with a system where under an octahedral ligand field, a transition metal having 4 electrons will have in order to exist as such. So now that is the first case. What about the case where the pairing energy is very little? It costs very little to pair electrons rather than traveling through the energy gap, which is your delta O. So it is now more easier to pair than to go up there because it means that the splitting energy would be too high. And as a result, electrons will not afford going to the higher energy level. And as a result, they will pair. So what happens when they pair? Let's go to the next slide. All right. That is called a strong field case, where now the splitting between the d orbitals induced by the octahedral ligand field is too large compared to the pairing energy. So electrons really now say we have to pay, we've got no choice. This is easily affordable. This is too expensive. Now we can afford that. And they sit together. We've got now the 4th electron pairing up with one of the electrons in the T2G. In the previous set, you've seen T2G was occupied by 3 electrons, all with parallel spins. But now the 4th one cannot occupy the same orbital with any one of these, with a spin going up. Go back to your Pauli exclusion principle, and then you'll see that that electron, the 4th electron, will have to pair or share an orbital with one of the existing electrons in the T2G, and its spin must be reversed. So that now, when you do that, you had 3 electrons. They had half a spin, all of them half. It's 3 halves or 3/2. Now you're bringing up another electron, now spinning in the opposite direction. It will be negative a half. So it will be plus a half and a negative a half. So you will be left with the spin state due to 2. So do you see that in this case now, 2 will be 2 electrons, which amount to the net spin of 1, because it's half plus half. That will give. And in the previous case, we had a spin state of 2 because we had 4 unpaired electrons. So you can see that in the present case, we're producing a coordinate, a configuration of lower spin than the other one. So because of the pairing, some spins get cancelled, and you're having a lower spin, and we call this a low spin case because there is pairing of electrons. Otherwise, parallel spins would maximize the spin state of the particular compound and its magnetic susceptibility, if you like, because unpaired electrons definitely generate a lot of magnetism, and you can pick that up by magnetic measurements. So I've got sort of a definition of the crystal field theory, which I think you will be able to go through and understand, because you are comparing the unsplit state versus the split state. That is the general thing. And I've got an exercise that I would like you guys to work. We've already taken one from here. This wants you to do all of them from D1 up to D10, up to where we've got all the 5 d orbitals occupied with electron pairs, because 5 times 2 will be 10. So we've already taken D4 here. So I think you can do the same. When we said D1, D2, and D3 are trivial cases, we know where the electrons are going to be. Those ones are insensitive to the strength of the ligand, if you like. We'll be defining a term like that as we proceed with this. So that's what we have now. All right, how do we get to measure this delta O, which is very informative because it tells us how distant the EG set of orbitals is from the T2G, or how significant the interaction between the ligands and the metal has been, because the interaction between the ligands and the metal brings about a splitting in the energies of the orbitals, having a 3 going down and 2 going up, and you call in the 2 EG, and you call in the 3 T2G, and the energy gap arising between the two. So how do you do that? One of the key features and the key criteria is to run spectroscopy. It's unfortunate that we're not doing labs, because you could have prepared complexes, you could have run some UV spectra on that, and UV is one of the most accessible techniques to characterize transition metals, because you've got DD transitions happening, or electrons, getting excited and relaxing within the D subshell itself. So very importantly, you run a spectrum, and in a spectrum, you'll find that there will be the highest point with because the signatures in the spectrum will be peaks, but not all peaks will be of the same intensity. So what you're doing is to take the peak of highest intensity and look at its, the wave number. It can be the wave numbers, it can be the wavelength. It depends on the mode of recording of your spectrum. Sometimes, in this particular case here, I've taken an example where spectrum has been plotted as a function of wave numbers, but wave numbers are derived from the wavelength. So a wave number, which is designated centimeter to the power -1, or per centimeter, if you like, it's essentially the reciprocal of the wavelength. So you're taking the wavelength if it is the wavelength, but in this case, it's essentially the wave number. So you can easily use that because the wave number represents the frequency. Remember that the frequency and the wavelength are inversely proportional. If you've got a long wavelength, then frequency would be low. If you've got a short wavelength, then the frequency will be high. So that inverse relationship is very applicable in spectroscopy here. You're looking at the spectrum of a compound. It's a coordination compound, octahedral compound, hexa aqua titanium 3 iron, where you've got 6 water ligands, if you like, and titanium in a 3+ oxidation state. And if you go to your periodic table, you'll find titanium just after scandium on the periodic table. It is in group 4 of the main, of the transition metals, which means that it is a D4 metal in its neutral state. But because it's now titanium 3+, it is a D1 compound. And as a result, there will only be one electron in the D subshell. And that electron in an octahedral field will occupy the T2G set. In the ground state of an octahedral complex of a titanium 3+, that electron is going to be in the T2G. And in order for you to see a peak or color or whatever, it means that electrons are making transitions between energies or levels of unequal energy. And as a result, what this means is that there is excitation of an electron from the T2G set. If you look at the bottom here, I've got the electron configuration in an octahedron would be T2G 1 and EG with 0. But if you promote that electron, if it goes through your delta O, which is the gap, the energy gap between the T2G and the EG, you have an excited state here, because the electron now, you've got no electrons in the low energy set, and you've got one electron in the high energy set. That's an excited state. So that is what really shows you a peak. It shows up, that electronic transition shows up as a peak when the spectrometer does its analysis. It shows up as a peak, and the maximum that you're seeing in that peak can be used to calculate your delta O. So I would like you guys to use the Planck relation, which is essentially what you have been doing in the previous courses as well. Use the Planck equation. Remember, the Planck's equation is the energy of a photon equaling the Planck constant, which is h, multiplied by nu, which is the frequency. Right? And here, the spectrum can come up as the wavelength, or it can come up as the frequency as such, which is given in wave numbers. So you can essentially use an alternative form of the Planck equation by saying that the frequency is always equal to the speed of light divided by wavelength. So you can use the equation in the form hc over lambda, and the 1 over lambda is already the point you have here, which is what you see where the maximum appears here. But I've picked it up and given you in this so that you can use it to essentially calculate delta O. Initially, you're going to get that in just kilojoules per mole of photons, if you like, but you need to convert that into kilojoules. I think third-year students would know what a kilo means, and they can be able to convert. And remember that if you've got anything in per mole, it really means that you've got the Avogadro's number involved in there. So please do that calculation and send me your result. Don't just cook. Oh, I didn't give the answer here. Okay, that would be good if I didn't. Please just work it out. And if you can't find the correct answer, just email that to me, or whatever solution you have. I can make a comment on that, or I can share with my colleague in the course to do that. So let us look at the other applicability of what we have just learned now, the splitting of the d orbitals. It is very important that the transition metals have color. Through your experiments, I think I gave an example of the permanganate, which is very intensely purple. And we have used it in labs for various reasons, somewhere as an oxidizing agent, somewhere as an indicator, somewhere as whatever. Copper 2+, which is very blue, looks like what we have on the slide here. The potassium dichromate, which is very orange in color. That's characteristics of transition metals and their compounds, that they are colored, but they can also conduct electricity, as I said. And so to explain that, or to explain the color of transition metals, we can essentially make an argument relative to the splitting of the d orbitals as we spoke. You look at this, you have got your solution of a transition metal compound, you shine white light. And as it goes through the solution, certain frequencies or a certain frequency from the incident light will be absorbed. And that will leave certain frequencies that are not absorbable. And those ones will recombine after after going through the vessel that contain your sample. So your sample will extract a certain wavelength, and obviously we won't have the same type of light that comes out. So the color of the light that comes out is what really strikes your eye to say that the eye is a detector. Now it says, oh, this looks blue, or it looks red, or it looks green. It's because when the sun showing light through that particular shade or whatever, certain frequencies have been absorbed, and then you're seeing the balance of that. So that balance is very important because it can tell you about what is happening in this molecule here. It can tell you how big the splitting was, or how large the splitting between the T2G and the EG set are, or was in that particular case. It's very important. It's an indicator. So we've got the diagram that I have here. It's a way of simplifying the color that you can observe from a transition metal solution. This is your visible light or visible region of your electromagnetic spectrum. You can see it ranges from 400 increasing like that up to about 750. I think in the lab we normally plot this up to 800 nanometers when we plot. When we plot spectra of transition, not even transition metals, but even organic compounds, we essentially using the same range. So you can see that this is an order of increasing wavelength. And remember that as the wavelength increases, the frequency decreases. So it means the energy decreases as we move from 400 going like that, but it decreases as we go like this. So the simple thing of visualizing this, if I were you, I would draw a circle and then draw 3 concurrent diameters. They should pass through the center of a circle. And then you can see, you can name them Roy Bev. That is a way of cramming this. If you say Roy may be the name of a guy, but you can say Roy Bev, then you know that, oh, Roy, the R will be red, orange, yellow, green, blue, violet. So, and when you look at the arrangement of the colors, it is such that where the 2 diameters cross, you're forming what the high school teachers used to call vertically opposite angles. That when 2 lines cross, you've got vertically opposite angles that are equal. And the information that you can get from here, what it gives you really is that if a compound absorbs red light, if your transition metal compound absorbs red light, and remember that red light is the least energetic, you can see is closer to 750 nanometers, or it's between 650 and 750 nanometers. So the frequency is really very low. So if it absorbs that, then it's going to appear green to your eye. When you see a green object, it means the particular thing that you're seeing that color associated with has absorbed a red color. If a solution absorbs an orange color, it will appear blue. If it absorbs a yellow color, it appears violet. And if it's just like that, now it's going to repeat. So this is what is called the color wheel. And the color wheel allows you to predict the color that will be observed if a specific color is absorbed. But it equally gives you a sense of the delta O, or the splitting parameter between the T2G and the EG orbitals, because what it does is, if suppose you know the yellow, which is a long wavelength thing, if you absorb yellow, you're producing light, or you leave frequencies that are more energetic, you see you're producing violet. But if a compound absorbs violet, it means that in order to flight an electron from the T2G set to the EG set, you need a very high energy. And as a result, after that energy has been absorbed by the compound, the remaining one will be of a weaker intensity, if you like. So this is essentially can be used to gauge the size of the splitting parameter. By looking at the color of the object, then you'll know what color has been absorbed. And if that color is more energetic on your electromagnetic spectrum, the values, the frequency of that will tell you whether you've got a large splitting of the d orbitals, or you've got little splitting or small splitting. This is very important as well. someone can say, if a complex absorbs a red color, then how will it look to your eye? Then you'll just look across. If they say an object absorbs violet, how will it look to your eye? Then you just go across. If it absorbs that, you just go across. But if it absorbs this, does it mean that the splitting is large or small? That is another question that you can be able to answer. So please, I would like you to get engaged in this and engage us as well, so that we both design a way of trying to help from a distance as the situation dictates right now. I've got this table here that is again based on the relationship between splitting and the pairing energy. And please, and double please, look at what happens if we've got the hexa-aqua iron 2, which is the first complex that I have at the top there. It's a D6 metal because it has got iron, complex because it has got iron in a 2+ oxidation state. The splitting, the ligands, the 6 ligands there, causes a splitting, which is 10,400 wave numbers. And the amount of energy that you need to pair electrons in iron 2 is 17,600, right? So you can see that it is more expensive to pair electrons in this case than for this, essentially, to travel, or for electrons to travel to the high energy level, because it costs only 10,400 to go to the high energy level. So in route, it will be very expensive, and a savvy student would put some money in the bank and say, oh, I'm not going to afford this, right? So that is with that. You see that if we have said that when we defined weak field, strong field, we have said that if the pairing energy is larger than the splitting, then the compound will be a weak field case, and it will produce high spin complexes because the electrons will be maximally unpaired. Now let's take a sister compound, hexacyanoferrate 2. It again has the iron in a 2+ oxidation state, because you've got 6 ligands. 6 times -1 will be -6. You're taking -6 to the -4, it becomes a +2. So you've got N2 in this case as well. So you've got 2 compounds of iron 2 with the same d electron configuration. But look at this here. The splitting energy is so huge compared to the pairing energy. And as a result, the electrons will prefer to pair. And as they pair, they reduce the spin, right? It becomes a low spin complex, because now you've got 6 electrons unpaired in the water case, in the aqua complex. You've got 6 electrons. Only the 6th one will pair, because you've got 5 orbitals. You've got 3 of the T2G and 2 of the EG. So the 6th electron will pair. So you'll have about 4 unpaired spins. But here, all the electrons will pair in the T2G. And as a result, you're producing a low spin complex because the sum of the spins will be 0. All the electrons will be pairing like that and canceling the spins of each other. And you've got a low spin compound. That is very important, that now, if you look at this compound here, it tells us, or these 2 complexes, it tells us that having the same metal ion, but varying the ligand, we are seeing very distinct and very important differences. The fact that the water, or as a ligand, is unable to cause pairing of electrons, but the cyano group is able to pair. It tells us that the nature of the ligand is a very important determinant of the splitting, the size of the splitting that will happen. See how much this, by just changing the aqua ligand to the cyano ligand, we have sort of tripled the value there, if you like, which is very significant. So it tells us that the cyanide has something that it does which far exceeds the aqua ligand. Let us look at the cobalt case below there. We've got 2 complexes of cobalt. They are all cobalt 3 complexes. Cobalt is in a 3+ oxidation state, and it's a D7. But when you change the ligand from a fluoride to an amine, You see what happens to the splitting. It becomes so huge. So if the splitting becomes larger than the pairing energy, then the electrons will prefer to pair, and you produce low spin complexes. So this says that the nature of the ligand is very important, right? So these are 4 factors that are in your textbook that affect the size or the magnitude of the delta O, or the splitting of the d orbitals under an octahedral environment of ligands. The first one is the nature of the ligands, which we've just seen from that table, but you need to just explain and see the roots of why is it that that happens, right? And the other one is the charge on the compound, or the oxidation state of the central metal. You've got a higher charge on the central metal, or you've got a lower charge. So what happens, what the variations of the delta O with that? The identity of the central metal is also important. If you look at the D block of your periodic table, you'll find that it is essentially made up of 3 rows. All right. You take the S block away from that central part, take the P block away, and just consider that. I think the first slide that Mr. Maswanganya projected had an extracted periodic table that shows you where each element is. So you've got the 3D, you've got what we normally call the first transition series that goes from scandium all the way to your zinc there. And you've got the second transition series, you've got the third transition series. So there are 3 rows or 3 periods in that block. So depending on in which block the element is, or the central metal is, you'll have differences in the delta O. That is what the splitting. Keeping the ligands constant, right? And using different metals. I think we've got something like that in this slide. I'll quickly run to it before we actually stop. The number and the geometry of the ligands is also important. So let's quickly, if it knows, but right. The nature of the ligands, we've seen that when we use the aqua or the water as a ligand, and we use the cyanide as a ligand on the same metal, we get in different splittings. So that is essentially a suggestive of the fact that we can make, or we can arrange the ligands according to their strength of splitting the d orbitals. Because each orbital, each ligand has got its own characteristic splitting that it causes on the d orbital. So we can essentially arrange the ligands according to their degrees of splitting the d orbitals. And if we are able to do that, we come up, or we produce something called the spectrochemical series. Ligands arranged according to their order of increasing splitting of the d orbitals when they are bonded to the same transition metal. So it means that all this, the list that you're seeing at the bottom here, being an example of a spectrochemical series, has been carried out spectroscopically on octahedral complexes of the same metal, right? If you're varying the ligands, then you should keep the metal constant, because otherwise you'll be getting contributions from different things. You don't want that. You want to be able to identify the culprit in each case. So ligands have got different degrees of splitting the d orbitals. And if you look at this, the main feature here that you can see is that we having at the bottom here, we're ranging all the way from iodide, bromide, sulfide, thiocyanide, we've got the chloride, we've got the azide, you've got fluoride, you've got urea, you've got hydroxide, you've got the oxalate, you've got the oxide, you've got neutral water, you've got the thiocyanide. Yes, look at the 2, please. I think this is what you guys were introduced to when you were dealing with the concept of linkage isomerism in your second year, right? There's pyridine, there's ammonia, there's ethylene diamine, there's bipyridine, there's phenol, there's nitro group, there's methanide, there's the phenolide group over there. You can see it's C6. That's a benzene ring, which is an ionic, if you like. And you've got the cyanide, and at the top, At the top, you've got a neutral molecule, CO, carbon monoxide. And if you are to think of my introductory slide, I said that, or it's written on that introductory slide, that the basic assumption of the crystal field theory is ionic interaction between the metal and the ligand. And from there, if you are to interpret this, it means that anionic ligands are supposed to be the ones that cause very large splittings. And experimentally, that is not found to be the case if you look at the spectrochemical series, because the weakest ligands are anionic. If you look at this, halide at the bottom there, you can see. And very strange enough, how do you account for electrostatics when you're using a neutral molecule like CO, carbon monoxide? So really, that shows that basic assumption constitutes a weak point, which we will have to revert to at a later stage and about it. So please, that is how ligands, every ligand has got its own way. And this table shows you that if you've got a chloride, you've got water, you've got ammonia, you've got the cyanide on the same metal, you can really deduce your own spectrochemical series here, if you like, because you can see that is the weakest, followed by this is stronger than that, and this is stronger than that, and this is stronger than that. So essentially, you can have your own abbreviated spectrochemical series here. It shows that the nature of the ligand is very important in determining the extent to which the will be affected by an octahedral environment. I think it's obvious with the charge that if you've got a very large charge on central metal, the amount of pull that it will have on the ligands will be very high. If you've got a metal in a 2+ oxidation state and the same metal in a 3+ oxidation state and the same metal in a 4+ oxidation state, and they interact with the same type of ligand, the forces of attraction, remember that the more positively charged something is, the more affinity it will have for negative charges. And as a result, there will be significant interaction with increase in the oxidation number. That is what you can pick up from this. And there are quite a number of examples in your textbook as well that will illustrate this. And some of them, I think, we will have to paste them on the blackboard to just get you going or get used to solving problems. We will put some questions. We'll try to find some time to do that. Right, where the metal comes from. If you just simply look at the summary that we have of this is the table that you see. Right, the green table shows you group 9 metals or transition metals, the cobalt, the rhodium, and the iridium, right? That is in orders from top to bottom. That's your group 9. And you can see fixing the ligands. The ligands are all the same. They are ammonia ligands, or the so-called amine. This is hexaamine something 3, and the metals are all in a 3+ oxidation state. So everything else is fixed except the metal. So the changes that you're seeing in the splitting parameter is due to the position of the metal in the periodic table. It is very important. And this has got a very strange consequence that as high spin, low spin complexes are only possible in the first transition series. That is when you start from, normally we're leaving scandium out, but you can start from titanium going up to the other side. Because scandium definitely has got one oxidation state, and as a result, doesn't really match the requirement of a transition metal, if you remember your previous course in the second year. So essentially, the more down a transition metal is, then the larger stuff is going to be. I think we can stop here for now if Mr. Masongani allows me. I think we've gone past 9 o'clock. I think our lecture was going to go to 9. Mr. Masongani.
Hello, Prof.
Yes, I think now we've gone past 9. Hello?
Yes.
Swangis.
You are left.
Swangis,
You are left with 3 minutes.
Am I right that we can stop here?
Yes.
Is it?
Yes.
Thanks for the generosity. Thanks for the generosity. Right. I would like our students to notice this thing, that the 4D and the 5D, that is the second and the third transition series, have got very large elements. Those elements or those metals have got large lobes of their orbitals, and they interact even with weak ligands to produce low spin complexes. Large splittings arise because of the intrinsic nature. I think they are familiar with the radial profiles and whatever. Their second year. Those essentially govern the way an orbit will interact with its neighbors in space. That's fine. Let me get to the other component, which doesn't need a lot of explanation. That if you've got more ligands, this is just the number of ligands and the shape of the compound you're doing. They can relate that to oxyhedral